So the title actually should be relativistic astrophysical jets, because I will talk on jets in general, a little bit about hydrodynamic jets and also about magnetized jets. What I want to do is that in the first talk today, I want to give you some general background on astrophysical jets. Specifically, talk about why do you think that these jets are relativistic, because that's what makes them special. They are relativistic, and there are many of the phenomena that we see comes from this relativistic behavior of the jets. So I will focus on that. And then in the second talk, I want to dive a little bit deeper into the physics of the jet. That will mostly be on the board. And then we'll go back to the global picture and talk about the different regions in the jet. And if we'll have time, I will try to add another topic, which is relativistic shock breakout. And why shock breakouts are important, because most of the, well, at least jets from collapsing stars, which give us gamma ray bursts, we don't see them initially. They're produced deep inside the star. The star is very opaque. And when the jet breaks out, the first light that we see is actually the shock that the jet is pushing ahead of it when it propagates in the star. As this shock breaks out, it gives basically this, what gives the first light. And there are important, let's say, phenomena that are happening here, that some of them we think we already have observed, and we're definitely going to observe in the future. So without further ado, let's start. So first, as I said, I want to give a little bit background about astrophysical relativistic jets. So relativistic jets are common in many astrophysical systems that involve compact objects. We will discuss that. They appear in a variety of systems that we know of. The largest jets that we know appear in active galaxies, AGNs. They range in sizes between tens of kiloparsec to hundreds of kiloparsecs and even megaparsec. You don't see this jet. Its length is about 2 megaparsec, which is roughly the distance, which is more than the distance between us and the Andromeda galaxy. Okay, this is a single jet that range from here all the way to Andromeda galaxy is even more. We know jets in TDE, tidal disruption events, when a star comes very close to a black hole in the center of the galaxy, get disrupted, and as it gets disrupted, jets are. So these are galactic jets. There are also jets in scales of stellar size, or actually solar system size. These are microquasar jets that are coming from black holes in the size of about a few solar, and their sizes are about AU or a few AU. You can see a movie of radio imaging of these jets. X-ray binaries also give jets, and of course gamma ray bursts, which we'll discuss a little bit about. Gamma ray burst jets look kind of like that. Okay, so it's not really a jet. So this is not really a jet, as you can see. This is basically a blip in the sky. How do we know that this is a jet? I will discuss about it. But all these things have a common feature, and this will be the topic of this part of the talk. So energies, sorry. So the jet carry a lot of energy from the center of the system, where the black hole or the neutron star resides. And what they do is basically that they put this energy very far from the origin. For example, in AGN, they carry about 10%, up to 10% of the total mass energy that is accreted onto the black hole. In gamma ray bursts, it's about 1% of that. This comes out to about 10 to the 50 ergs per second. Now, if you take this amount of energy inside the star, okay, this is about the total energy that this jet carry, okay, is something like the entire bounding energy of the star. Now, if you try to put that in a spherical explosion, these things will have hard time to get out. Now, if you focus it in a very small opening angle, and then you shoot it out, it will push out from the star and it will break out of the star very easily. So that's the significance of the jet. They take all this energy, put it in a very small opening angle, and they just dump it in very, very large distances. Now, the way that they do that is they do that through extended cocoons. It's very hard to see it in the light, but this is the jet, and as the jet pushes through the medium, it develops like a very elongated cocoon, which this cocoon is basically a bag that holds the entire jet energy. The jet propagates, it dumps its energy into the cocoon, and it's continuing to propagate, and when the jet dies, all this energy becomes stuck into this cocoon, and through this cocoon it's getting distributed to the surrounding. So this amount of energy in galaxies, for example, if you take very powerful jets, which energy is about 10 to the 46 ergs per second, the lifetimes of the engines are about 10 to the 7 years. So 10 to the 46 ergs per second, in 10 to the 7 years, this comes out to about 10 to the 60 ergs. Okay? The entire gravitational potential energy of the Milky Way, including the dark matter, is about 3 times 10 to the 60 ergs. So the energy that the jet carries through the lifetime of the engine, the relatively short lifetime of the engine, sums up to about the entire gravitational potential energy of the galaxy. In GRBs, it's a similar thing. This is a picture of a jet in a GRB breaking out from the star. Okay, we have a star that collapses. The collapse forms a black hole at the center of the star, and from this black hole, the jet shoots out. The jet first propagates in the envelope of the star. This is the cocoon that I told you about. Okay, it takes the jet to break out about 10 seconds or so. So the entire energy that is locked inside this cocoon is about 10 to the 50 times 10, which is 10 to the 51 ergs. Okay, the gravitational energy of a star with a 10 solar mass and a radius, this is a typical Wolf-Rayet star, which are these very heavy stars that we think that produce the gamma ray burst. So at the end of the life of this star, it got several tens of solar masses around it. And the gravitational energy of this, the gravitational potential energy of this star is about the energy that the jet dumps into the envelope. So the jet has enough energy to disrupt the entire star. Okay, so that's a lot of energy. Okay, so let's focus a little bit about active galaxies. So what I want to do now is I want to talk a little bit about the observation, what we see in the jets, and from what we see, why do you think that, how do we conclude that these jets are relativistic? So a little bit about AGN observation. So AGN's observation is basically a zoo. We have all types of galaxies that show all types of different features that we call AGNs. The main feature that separates, the first feature that separates them, and in my mind is the most important one, is whether they have jets or don't have jets. Since we're talking about relativistic jets, I'm not going to discuss all these types of AGNs that do not show jets. So in these types of galaxies that do show jet, they have several different observational types, which basically we think that they are separated by the angle through which we view the jet. Okay, so if this is the torus or the disk around the black hole, this is the black hole, and this is the jet coming out of the galactic plane. This is the galactic plane. If you have an observer that is located around here and is watching the jets from the side, what it will see a jet coming out. Okay, and these types of galaxies are known as radio galaxies. Why are they called radio galaxies? Because these jets were first observed through the radio. Okay, they're definitely not only emitting radio waves, and as we're going to see, these types of galaxies are divided in also to subtypes, which are called FR1 and FR2. Okay, the jets are the classification through that is the morphology of the jet. We will get to that later in the talk, so that's why it's important to me to present it here. FR2 jets, which you hardly see here, but here you have a jet coming out. These are very, very long, very narrow, very straight jets. They are stable over hundreds of kiloparsec to megaparsec scales. Okay? They exhibit strong backflows, and they're seen mostly in field galaxies, galaxies that are outside of galaxy clusters. FR1 jets that you can see here, you see that the jet looks different. It's much more it's wider. It's also shorter. They tend to break at about tens of kiloparsec away from the center of the galaxy. They blow large, very large cocoons around them. And these types of jets are mostly seen in inside galaxy clusters. Okay? FR2 jets, which are these, are typically more powerful than the FR1s. Okay? So these are radio galaxies. If we move, closer to the jet axis, since the jet move at relativistic velocities, and not only that, it is very luminous, we will start to, when we view at smaller opening angles, basically what we will see something that looks like that. Okay? We do not see a jet anymore. What we see is something that looks quasi-stellar. So quasi-stellar objects are, short names are quasars. Okay? The reason that we know that these are not stars is because the spectrum is completely different, the stellar spectrum. We're going to show a spectrum of the quasar soon. Okay? If we are further closer to the axis, actually on the axis, what we see is something that is even more extreme, and these are known as blazars. Okay? So blazars are just quasars that we see exactly along the axis. What we see in blazars, when we look in radio, we see blobs, and this is a blob coming out of the center of the galaxy. It moves a little bit to the angle because we're not exactly on the angle, we are a little bit to the side, so what we see is something that moves on the line of sight. But the important thing is that these things seem to move at velocities that are faster than the speed of light. Okay? So if we track the distance that this blob is doing across the sky, and we take the time through which it moves, we will get velocities that are larger than c. Okay? And these are known as superluminal velocities, and this is the first thing that I'm going to talk about. Before that, this was about radio galaxies. GRBs are jets that are coming from stellar-sized objects, not from the galactic center. And GRBs are kind of like blazars. We're basically looking at them very close to the axis. Okay? So that's why what we see is we see this point, we see this blip. Okay? Okay, so let's talk a little bit about superluminal motions and why do we think that from superluminal motion do we think that that things are moved at relativistic velocity. So here is an image of blazar 3C279. So this blazar at 90, and this is 98. So within 6 years, the motion across the sky, this range from about 20 light years, and this is 40 light years. Okay? So within 6 years of observation, this blob moved from about a distance of about 20 light years. So quickly calculate in your head what is the velocity that comes out of it. Okay, so this is about 3c, exactly. Okay, I heard someone whisper that. You can talk. It's okay. You can talk. You can vote. And don't be afraid to ask questions during this talk, because some of the stuff here is trivial to some of you, but some of you hear it, I guess, for the first time. So it's sometimes it can be a little bit hard to follow. So this blob seems to move at a velocity which is 3c, which is impossible. Okay. So how does this happen? Let's take for example, this toy model. So this is the center of the blazar. Okay, the observer is looking over here, and here we have this blob, and this blob is going to shoot out at an angle of theta from the line of sight. Okay. Now, at the moment that this blob will leave the center of the galaxy, it will emit its first photon. So every photon that hits the observer is an observation. Okay. So the first photon will represent the first image. And okay, so here's the photon coming to the observer. And now when this blob is reaching to this location, it emits the second photon, and the second photon will be this observation. Okay? Now the time that passed between these two observations is basically the time that passed between the emission the time that is basically the distance between these two photons at the moment that this blob emits the second photon divided by c. Okay? So let's put it in a plot and let's explain. So at the time of the launching, this photon is moved at a velocity of c, and by the time that the blob reached to this location, the distance that this photon covers is c times delta t. Okay? Simple. Now, this blob moves to this location at the velocity v, which is smaller than c, because nothing can move at a velocity larger than the speed of light. And at the time when it emits the second photon, it moves a distance along the line of sight, which is v delta t times cosine theta. Okay? So this distance, c delta theta observed, is just c delta t minus v delta t times cosine theta, and I take c delta t out of the brackets, and I get 1 minus beta cosine theta. Now, beta is just the velocity divided by c. Okay, I will use beta a lot in this talk, so beta is just v divided by c. Okay, it's a unitless quantity, and it's always smaller than 1, and that's important. Okay, so now what we see, okay, we do not see this. What we see is the sea motion across the sky, right? We see this blob move across the sky, so this is the distance that we see. Okay, so the observed velocity across the sky is basically this distance, v delta t sinus theta, divided by the delta t that we see that passed between the arrivals of these two photons. So it's v delta t sinus theta divided by delta t observed. Okay? And again, we just put what delta t observed is, and we get to this expression, beta sinus theta divided by 1 minus beta cosine theta. Okay? Now, if you will plot this quantity, okay, and this is what I'm doing here. Sorry, if you will plot this quantity, what I'm plotting here is v perp observed divided by beta. So what I'm plotting in this quantity, sinus theta divided by 1 minus cosine theta. Okay? What you see is you see a graph that looks like that. When theta is 0, what does it mean theta equal to 0? Where are we located on the axis? Exactly on the axis. When theta is 0, the jet is pointing directly at us. Okay? So when theta equals 0, you can see that there should be no motion across the sky, right? Because everything is pointing toward us. And indeed, beta perp is 0. Okay? When we are located at theta equal 90 degrees, okay, what we will see, the entire motion across the sky is basically the actual motion. So what we should see is the actual v, is the actual velocity of the blob. And indeed, when theta is equal pi divided by 2, okay, this thing is equal to 1. So beta observed divided by beta is 1. So beta perp observed is just beta. Okay? At any angle between 90 and 0, okay, we should see a beta observed which is actually larger than beta. Okay? And the peak of this velocity is obtained when theta is equal to 1 over the Lorentz factor. Does everybody know what Lorentz factor is? Anybody doesn't know what Lorentz factor is? Okay. So, good. So we're in a good place. Okay. So, so the peak of this distribution is coming when theta is equal to exactly 1 over gamma. And in this peak, the value is just gamma. So the observed velocity is the Lorentz factor, and the Lorentz factor is always larger than 1. Okay? So, and at any other angle that we see, we'll see something that is a little bit smaller than that. So if we'll do a quick math, and we try to calculate what is the Lorentz factor, so just by viewing this, okay, just by viewing a superluminal motion, I can get a constraint on the actual Lorentz factor of the material in the jet. Okay? So if we have something that in 6 years moved a distance across the sky of about 20 light years, what is the Lorentz factor? Yes? What did you say? Exactly, more than 3. So the minimal Lorentz factor is about 3. Why? Because if we were located at an angle that is exactly 1/3, we would see beta perp equal 3. But we're likely somewhere around here or somewhere around here. So what we see is actually a beta which is smaller than the actual Lorentz factor. Okay, we see the observed beta, which is translated to a Lorentz factor, is something that is smaller than the actual Lorentz factor. So what we have is actually a lower limit on the Lorentz factor. So it can be 3 or more. Okay? Okay, so let's talk about the spectrum. We said that quasars are quasi-stellar objects. Why they are quasi-stellar objects? Because the spectrum is completely non-thermal. Okay, this is a typical spectrum of a blazar or a quasar that we see. Just to give you a translation, this is the frequency in units of hertz. If you want to translate that to electron volt, you just need to multiply it by about 10 to the minus 4 times 10 to the minus 15. So this peak around here, this is around 1 eV. So 1 eV is in the UV. Okay. 10 to 18 is about keV, which is X-ray. Okay, so this is X-ray. And everything you see around here are basically gamma rays or TeV energies. Our GeV and TeV energies are around here. Okay, so you can see that the spectrum range takes the entire wavelength. And this is completely non-thermal spectrum. Just to give you an idea how does a thermal spectrum look like, this is a thermal spectrum. Okay? So if we would have observed a star at the location where this quasar is, this is the typical type of a spectrum that we will see. This is completely non-thermal. Okay? So usually in order to model these spectra, what we think is that happening is that the first bump is coming from synchrotron radiation, and I will talk a little bit about synchrotron radiation, while the second bump is coming from inverse Compton. Okay? So in a synchrotron radiation, what we have is we have an electron that is orbiting around, that is moving and rotating around some magnetic field. Okay? And as it rotates, it accelerates. And as it accelerates, it emits radiation. Okay? Now, the typical power of a synchrotron, sorry, let's start with the typical frequency. So the typical frequency of the synchrotron is a product of the magnetic field, okay, times the Lorentz factor square of the electron, okay, times the Doppler factor, the Doppler shift. The Doppler shift comes from what we have is that, remember, we already figure out that there is likely some relativistic motion in the jet. So when we have relativistic motions, we separate it into two types of motions. Okay, we have the bulk motion, the motion of the entire plasma as it moves roughly toward us, and this I usually mark with large gamma. Okay, and this is the Doppler factor of the bulk motion of the flow. Okay, and inside the flow, if the particles are accelerated to relativistic velocities, we have random motions of the particles, which it can also be relativistic, and this is the small gamma. So this is the gamma of the electron. So we have two types of Lorentz factor here. Okay, so the synchrotron frequency is coming from is basically obtained from both the random motion of the electron and the bulk motion of the entire flow. Okay, and the total luminosity, you can just open Rybicki and Lightman and see how it works. The only thing that added here is also that the Doppler factor squared here. Okay, so we have a boosting in the luminosity by a factor of d square. Okay, so this will give us the first peak in the spectrum. Okay, now for the second peak, what we think is happening is that if we have an electron and the electron is emitting a photon, now these photons can be scattered onto another electron. Okay, so this process is called synchrotron self-Compton. So the electrons within the blob are emitted from electrons, and on the way that they're leaving this blob, they are scattered on top of another electron. And when they're scattered, they're getting boosted. Now, why are they getting boosted? So if we have so imagine that we had an electron, okay, and the electron emitted a photon, okay, and with some typical energy. Okay? And this electron moves at a Lorentz factor gamma. And there is another electron within this blob that is also moves at a Lorentz factor gamma, okay, because the random motions of the electrons is gamma, sorry. Okay? Now, within the rest frame of this electron, what is the energy of this photon? Misha, you don't need to say. It's for the students. So, when something within, if I'm moving toward you and you're emitting a light, okay, if you're moving toward me, sorry, and you're emitting a light, and I'm watching the light, this light is boosted because it has a Doppler shift, and the boost will be by a factor of gamma. Okay, so within the rest frame of this electron, okay, what it sees, it sees a epsilon tag, which is equal to epsilon times gamma E. Okay, this is what electrons see. This electron see. Now, this electron absorbs the light and it emits it at some random direction. Okay, so the electron emits the light, and since energy is conserved, this light is emitted by the same energy. Epsilon tag is equal epsilon times gamma electron. Okay, now we need to move back to the rest frame of the flow. Within this rest frame of the flow, this photon is moving by a velocity of beta, by a Lorentz factor of gamma. So we get another boost by a factor of gamma. Okay, so within the rest frame of the blob, this photon has now an energy of gamma square times the original epsilon. Okay? So a single kick within the rest frame of the flow will give us a factor of gamma square. Okay? Now, this thing will also be boosted by the same Doppler factor because we're still in the same blob. But now it is boosted to a factor of gamma square. Okay? So the second peak should be different from the first peak by a factor of about gamma square. Was this clear enough? Good. Okay? So we have a first observable. Okay? Within this model, if I know the location of the first peak and I know the location of the second peak, I can tell what is the Lorentz factor of the electrons. Okay? Over here, the difference is about 10 to the 8, so the Lorentz factor should be about 10 to the 4. Okay? The second observable that we see is the difference in the height of the curves. So the height of the curve, yes?
How many scatterings do you have?
Good question. The number of scattering depends on the optical depth. Okay? So usually you have a very low optical depth, so a very low optical depth is an average less than one scatter. Okay? But true that as the optical depth becomes larger and larger, you should see more and more peaks. Okay? Let's talk now about the optical depth. So what is an optical depth? Everybody knows? Someone want me to repeat? Don't be shy, I will repeat. Okay? Oh, someone nodded, so an optical depth, okay? So tau is basically the average number of scattering that the photon will undergo as it moves through some region that contains gas or anything that can scatter it. So the way that optical depth is defined is basically the density of the scatterer, okay, which is, the units are 1/centimeter cubed, okay, times the cross-section of a scatterer that is usually known as sigma. Okay, so cross-section of the scatterer, here is my photon, and it moves through this blob. And over here, I have many scatterer on the way. Okay, the cross-section is just the area of each scatterer, so the units here are centimeter square, okay, times the distance. So this is r. Okay, times r. So this unit is centimeter. So you see that the value of tau is unitless, it has no unit, and it basically represents the number of times that these photons will be scattered as it passes through the blob. So usually in astrophysical system, tau, let's say, is smaller than 1, unless you're in dense, very dense region, like inside of a star, when this way tau is much larger than 1. But so if a radiation is moving through a blob like that, and photons are scattered all over the way, so anything that comes in, what comes out will be less. Okay? So when we look at the luminosity, the energy per unit time of the second blob, it should be affected by, it should be boosted, okay, by a factor of gamma square, because that was the boost of the photons, of each photons, right? So it was be boosted by a factor of gamma square. But it should be also, some of the energy was depleted, and the amount of energy that was depleted is a factor of tau. So the difference of heights between these two bumps will give us an information about the density of this system. So that's a second observable. Okay? So this will give us an information about the density of the electrons, which are the scatterer of these photons. Okay? And the last thing, that if I want to know what is the Doppler factor or the bulk motion of the flow, all I need to do is I need to apply some model on the emission. Okay? So over here, I already know what gamma electron is. I need to assume something about the magnetic field, and if I assume something about the magnetic field, this immediately will give me the Doppler factor. So within this simple model of synchrotron self-Compton, if I assume something about the magnetic field, just from the observation, I can tell what is the Lorentz factor of the electron, what is the bulk motion, and what is the energy density, what is the number density of the particles that are scattering the radiation. So it's a very nice model. Only problem is that no one assured that this is the correct one. Okay, so you need to take that within a grain of salt. So that is second. So this is a second mark that the velocities are relativistic. Okay. The third thing that I want to talk about is variability and something which is called the compactness problem. Okay. So when we look at light curve, before what we observed was spectrum, was the power as a function of the energy within a snapshot. Now what I'm looking at the light curve. I'm looking at the energy as a function of time, as it changes with time. And this is a light curve from a quasar. This is actually a blazar when we look into the jet. And you see that the light curve double its power over time scales which are about 5 minutes. So what we say is that the variability of this thing, delta t, over here it is much, much smaller than 1. And the typical time over which this light curve changes is about 5 minutes. In gamma ray burst, when this is a typical light curve from a prompt emission, from the event that takes about, I don't know, you see here it takes about 80 seconds. Okay, so the entire event took about 80 seconds, and within this 80 seconds, you see all these very, very narrow lines. This is a variation of the light curve, and the typical variability time here is between millisecond to a second. Okay, so what does this thing tells us? So if we have an object, okay, and this object, let's say, is at rest, and let's say that something happened within this object and it's emitted a light. Okay? So light is coming from the entire surface of the object. Okay? So as an observer, okay, the time that passes between something global happened within this object. Okay? So there was a blip or something, a burp, and light emitted throughout, an instant light. Light was emitted instantaneously from the entire surface of the object. Now we as observers, we are located around here. Okay? So what will be the duration over which we will see this instantaneous pulse as it reaches us? What will be the duration that this pulse will be observed here?
The size of the object divided by c.
Exactly, because we see light that is coming from here, but we also see light from here is emitted not only in that direction, it's emitted at half a pi direction. So photons that are coming from here as well, okay? And the distance between these two photons is r. So the time that passes between the arrival time of this photon and the arrival time of this photon is just R divided by C. So by looking at delta T, what we can get is a constraint on the size of the object. The problem is that when you look at this variability time, the constraint of the size of this object, let's say that this 5 minutes is about 300 seconds, so the constraint of the size of this object is about 10 to the 13 centimeter. So what is the problem? That in quasars, in galaxy, in AGNs of this type, the sizes of the black hole range from about 10 to the 8 centimeters all the way to 10 to the 10 centimeters. And the brighter they are, the larger the black holes are. So what is the size of the event horizon of a black hole with a mass of about 10 to the 9 centimeters? Okay. What is the, let's do that. So what is the radius of the event horizon of if the sun would have collapsed to a black hole? What would be the event horizon size, the Schwarzschild radius of the sun? What is that? Do you know? It's about 1.5 kilometers. Okay? So it's 10 to the 5 centimeters. Okay? So one solar mass is 10 to the 5 centimeters. Now the radius of the event horizon scales like the mass. So we have 10 to the 9 centimeter. So what will be the size of the event horizon of a black hole with a mass of 10 to the 9 centimeter? It's 10 to the 5 times 10 to the 9, which is 10 to the 14. Okay? So if we want this to be if we want this to represent the actual size of the event horizon of the black hole, which is the smallest size in the system, okay?
You said mass in centimeters, that's why people were confused.
Sorry?
You said mass in centimeters, that's why people.
Okay, yeah, I get mass and size in black holes are the same. Okay, so when I say one solar mass, I mean 10 to the 5 centimeter. When I say 10 to the 9 solar mass, this is 10 to the 14 centimeter. So the size, and a variability of 100 seconds represents length scales of 10 to the 13 centimeters, which represents a black hole with a mass of 10 to the 8 solar mass. This is the smallest size black hole that we can think about, and this is a very luminous quasars, and the masses here are ranged between 10 to the 9 to 10 to the 10 solar masses. So it means that this event, whatever happens, came out from something that is the size of 1/10 of the size of the black hole. And the energies are enormous. So this is completely ridiculous. So it means that I will take the entire energy that is emitted from the black hole, and I will focus it in a region with the size of 1/10 of the event horizon of the black hole, and this is completely impossible to do. Okay, so this is one problem. Another problem that we see is that this variability, which represents a size, and to remind you, the size also coincides with the optical depth. Okay, so now I'm going to explain you something that is known as the compact problem, compactness. And the compactness problem is coming from the fact that we observed photons with very, very high energies. Okay, the photons that we observed are in MeV, GeV, and even TeV energies. Okay, now as you know, photon-photon interactions produce pairs. Okay, now what is the optical depth to produce a pair? So this is just the Thompson cross-section times the density of the photons that can produce the pairs times the size of the system. Okay? Now the size of the system, as we can see, we can extract from the variability. Okay? The density of the photons is just the total energy within the event, which is basically the integral of that. Okay? Times the fraction of photons that can produce the pairs, which are all the photons with energies that are larger than MeV, okay, divided by the volume and divided by the typical energy of a photon that produced the pair. So let's suppose that all the photons are at MeV at the moment. Okay, so this is total energy divided by volume divided by energy. This gives it a number density. Okay, so this is the number density of the photons that can produce pairs, and sigma Thompson we know. So we put all of these together. What we get is a number which is this high. This is 10 to the 13, so each photon, if I'm looking at a typical gamma ray burst, with a typical, so you see here what we have is that this is E times, because this should be a unitless, this should be a unitless number. Okay, so what we come out from E divided by T is basically the luminosity of the object. So the luminosity of the object in gamma ray burst is about 10 to the 50 ergs. Okay, the typical duration over which the event is happening is about 100 seconds. Okay, so what we get is a number of about 10 to the 13 centimeters. So within gamma ray burst, within the blob, each photons that can produce pairs will be scattered 10 to the 13 times with other photons that can produce pair before it will leave the blob. So is there any chance for a photons with an energy larger than 1 MeV to leave this blob? None. Okay, so any photons with energy larger than MeV will produce pairs. Okay, so the spectrum this is basically a black body. Okay, black body is defined by infinite number of scatterings of photons as they come out from the surface of the black body. So the spectrum that we're expected to see is a black body spectrum. In the case of quasars, the luminosity is about 10 to the 36 erg per second, 10 to the 44 erg per second, okay? And the durations of the events, let's take this event for example. So this duration is about 100 seconds, okay? So this delta t will be multiplied by a factor of 4. So as it comes to the power of -1, so we need to take power of 4 from his. The luminosity is reduced by another factor of 4. So we should subtract 8 from this, so we will get 10 to the 7. So the optical depth in this event should be around 10 to the 7. Again, a black body. Okay? We don't see a black body. As I showed you in gamma ray burst spectrum, also the spectrum is completely non-thermal. So this is a problem. How can this very small variability coincide with the spectrum that we see? This is the compactness problem. So how can we solve it? So in order to solve it, I want to talk to you a little bit about relativistic effects. Okay, because relativistic effects will solve the problem for us. So assume that we have some source. Here is the source, and the source is emitting photons, and the source is moving toward us with some velocity which is close to the speed of light. Okay, so what I want to do is I want to measure to understand the distance that this source covers between the time it emits this photon and the time that it emits the second photon. Okay, and so the time that passes between the emission of these two photons, this is my delta t observed. This is the delta t that I observed. Okay, so again, the distance between these two photons, like we did before, is c time delta t that we observed. This is the distance between these two photons. The distance that the first photon covered, the actual distance that the first photon covered by the time that the second photon was emitted, is c delta t. Okay, and the distance that the blob moved between the emission of the first photon and the emission of the second photon is c times beta times delta t. Okay, so delta t observed is just c delta t minus c times beta delta t divided by c. Okay, so here again what we see is this factor of 1 minus beta that we saw before in the superluminal motions. Only here, since all motions are along the line of sight, cosine theta is 1, so that's why there is only 1 minus beta. Okay, 1 minus beta, if I want to switch it to talk in Lorentz factor term, so beta is square root of 1 minus 1 divided by gamma square. If gamma square is very large, then this is approximated to 1 minus 1 divided by 2 gamma square. So I take that, I put it over here, and the ones are cancelled out, and what I get is delta t divided by 2 gamma square. This is an important quantity. Why? It means that if the time between two pulses within the frame of the star is compressed by a factor of gamma square when I observe it from a distance, if the motion has a Lorentz factor of gamma. So this is called as observed time compression. Okay, relativistic time compression, and of course the radius that I will obtain from that, naively, is just delta t observed divided by c, which is very small radius. But since time was compressed, the radius within the emitting system will be c delta t observed times gamma square. Okay? So if the Lorentz factor is about 100, the radius will be multiplied by 10 to the 4. Okay? So this is a much larger radius. Much larger radius is smaller optical depth. Okay? Because the density will be smaller. Okay? To remind you, I had here in the optical depth expression, okay, because I have distance, sorry, I have that here, because I have distance, sorry, divided by density, each of them has will be larger. This will be larger by factor of 1,000. This will be smaller by a factor of 1,000 cubed. Together, I will have a reduction by a factor of 1,000 square. Okay? So this is the first thing. Now, there is another way to show that. And remember that we talked about a spherical shell. Okay? Now, if I have not an object that is moved toward us, but a spherical shell that is expanding, okay, and it emits its photons instantaneously, okay, so here I will have something that is known as relativistic beaming that will come to my aid. I'm going to explain relativistic beaming soon, so you can understand what's happening. But what's happening is that if this shell is moving toward us, then every photons that is emitted from every point in the shell, all the photons will be beamed into an opening angle of theta, which is equal 1 divided by gamma. I no longer have, if I have something that moves toward me and it's emit light, within its rest frame the light is emitted in 3 pi, like isotropically. But if I'm looking at it from in the lab frame, half of the light will be beamed into a cone with an opening angle of 1 over gamma. Okay? So if I'm located around here, okay, I will only be able to see regions with photons that the 1 over gamma cone of them intersect with the line of sight. Okay? These photons will be emitted into 1 over gamma, but it will never reach me because it's out of my line of sight. So I will only see regions within opening angle of 1 over gamma here. Okay? So I will see these photons. I will see this photon coming from here, and I will see these photons where theta is equal to 1 over gamma. So again, the distance between these two photons, if these photons are emitted instantaneously, the time difference that they reach me will be this distance, which is equal to, this is r, so r divided by c minus r cosine theta minus this part divided by c, which gives me this part. Okay? So delta t observed will be just r divided by t times 1 minus cosine theta, and so this is r theta squared divided by 2c. Now, if theta is equal to 1 over gamma, and 1 over gamma is very large, so theta is very small. So cosine theta, which is very small, okay, I can approximate to 1 minus theta squared divided by c, so that's why, divided by 2, sorry, so that's why I have theta squared divided by 2 here. And since theta is 1 over gamma, what I get is that r divided by 2c gamma. So again, the factor of reduction of gamma square here, r divided by 2c gamma square. So this means that the total r, which is equal to the true delta t, will be multiplied by 2c gamma square. Okay? So the total radius here is just is the delta t observed times gamma square. So it is larger by a factor of gamma square. Now, before I move to the second part, do you want me to explain to you the relativistic beaming, or do you know relativistic beaming? Do you understand where it's coming from? Why the emission in the rest frame, which is isotropic, is beamed into a cone of 1 over gamma? Anyone dare to explain? Okay, so I will take that as please explain to us, but we're too shy to ask. So a few words about relativistic beaming. Okay? Okay, so I actually have a slide. So, relativistic beaming. Let's take an object that is moved at an angle of theta from the line of sight. The line of sight is along the x direction. And it moves within a system, O tag, that moves with the velocity of v towards the observer. Okay, this is the moving system, and within this system I have an object that moves at an opening angle of theta. Okay, so we are located here, we have the observer, and this system, we are in the lab frame, and I want to ask what is the opening, what is theta in the lab frame. Okay, so I have the velocity u, okay, and I can decompress it into two components, a perpendicular component and a component along the line of sight. Okay, so uy will be the Lorentz transformation of the velocity in the perpendicular direction is this. The Lorentz factor of the velocities along the line of sight is u tag times v divided by this factor. Okay, so the opening angle tangent theta in the observer frame, okay, is just uy divided by ux, which gives us this expression. Okay, now if you see that there is a Lorentz factor here, and this is theta tag. Okay, now if we take the extreme case where the motion is exactly perpendicular, so theta tag is equal to pi over 2. So sinus pi over 2 is 1, cosine pi over 2 is 0. What we get is that tangent theta is 1 over gamma beta. Okay? So if gamma is very small, this implies that theta, if something is emitted at an angle of 90 degrees, the observed theta will be just 1 over gamma. So everything that is emitted within the rest frame at an angle of 2 pi will be compressed into an opening angle of 1 over gamma in the observer frame. Where are all the rest of the photons going? Where are all the photons that were emitted here? How are they distributed? Not just backward, outside of the 1 over gamma. But what this means is that the energy density, half of the energy density of the light is concentrated to a very small opening angle. The rest is just distributed at a very wide opening angle. So since the energy density is small, the light that we will see at angles that are larger than 1 over gamma is diminished by much. So we basically will see a beaming. Okay? It's like a flashlight. Okay? So that's why I have this cone of 1 over gamma that is coming from every part of this blob that is expanding isotropically. So I will only see the parts of the cone that is pointing, the parts of the sphere that is pointing toward me. Okay, that's relativistic beaming. Okay, so we are back in the compactness problem. One problem we solved, the size of the emitter. We still have another problem. Remember that I told you that I still have a very large optical depth. Only the size will not solve it. I have 10 to the 13 centimeters. Now, if I have a Lorentz factor of 100, this takes out 10 to the 4. This takes out 100 square. So I'm down to about 10 to the 9. But I'm still not out of the woods yet. Okay? There is a second something that comes to my aid, and that's the fact that the energies of the photons within the rest frame of the blobs are different than the energy photons of the photons that we see. Remember that I see MeV photons, and I have a blob that is moving at the Lorentz factor of 100 towards me, so it means that within the rest frame of this blob, the energies are smaller by a factor of gamma. Exactly. So the energies are smaller by a factor of a gamma. Now, I have photons with energies that are smaller by a factor of a gamma that are scattered on one another. Okay? So remember that in order to produce pair, there is a threshold. I need the multiplication of the two photons that collide with each other to be larger than me squared times c to the 4, than the energy density of the electron squared. Okay? So suppose that I have a spectrum within the rest frame of the blob, and this spectrum looks kind of like that. The number of the photons scales like gamma to the power of minus alpha. Okay? If the blob was at rest, all photons with observed energy of MEC squared, all photons with energy larger than the dust will produce pairs. So all of this will not be observed because all of this will produce pairs. Okay? So now, but if now these things move at relativistic motion, then the energy of the first photons within the rest frame is lowered by a factor of 1 over gamma. Okay? So what will be the energy, what is the minimal energy of the scatterer that I need in order to produce pairs onto that photons? So it's just m to the power of 2 times c squared divided by the energy of the photon in the rest frame. Okay? I just substitute E1 times gamma. So I get that the energy, the minimal energy of the photons within the rest frame of the blob that can produce pairs from these photons is multiplied by a factor of gamma. Okay? Now these photons, remember, is existing in a blob that is moved at a Lorentz factor of gamma toward us. So what will be the observed energy of this photon? This is the energy of the photons within the rest frame of the flow. What will be the observed energy of the photon? Multiplied by a factor of gamma. So the minimal energy of the photons that can produce pair now is gamma squared times m electron squared times c to the power of 4. Okay? So if I have a photon with an observed energy of gamma ray, which is MEC squared, which is basically half of MEV, okay? The observed energy of the photons that can be scattered on top of it is gamma squared times MEC squared, okay? So the fractions of photons that will be scattered on top of these photons that are observed at MEV, right, is over here, is now moved by a factor of gamma squared. Okay? So the fraction of photons that can scatter these photons is now the original Fe times, okay, gamma to the power of minus 2 alpha. Because gamma squared, the spectrum has a slope of gamma to the minus alpha. So the area here is smaller than the original area by a factor of gamma to the minus of 2 alpha. Okay? So if gamma here is 100, and alpha, let's say, is about minus 2, so because this is the typical spectra that we see. So this factor would be reduced by a factor of 100 to the minus 6. This is a huge factor. Okay? So if now we conclude, if the blob is moving at relativistic velocities, two things happen. First, it is larger by a factor of gamma squared. Second, the optical depth to produce pairs within this blob is smaller by a factor of gamma to the minus of 2 alpha. So the actual optical depth, okay, we have here, remember, gamma squared, and we have here also the fraction of the photons that are produced the pairs. So here I have a total factor of gamma to the minus 4 times alpha, okay? Remember, I had gamma to the minus 2 plus alpha plus gamma to the minus plus gamma to the power of 2 here. So I have gamma to the minus 4 plus alpha. If alpha is 2, I have gamma to the minus 6, okay? So for an optical depth of 1, remember I started with 10 to the 13, with optical depth of 10 to the 13. If I take a Lorentz factor of about 100, then I'm down to an optical depth of 1. So this is the reason, if you watch a spectrum, a photon from a gamma ray burst, okay, and you assume that all the scatterer of this photon come from a single blob, all I need to do is to watch at the highest energy of the spectrum that I see, and this will give me a lower limit on the Lorentz factor that the blob is moving. So if I watch MEV photons in gamma ray burst, okay, and I see variability of about a millisecond, it means that the Lorentz factor of the motion of the blob, of the jet, is about 100. Within these quasars, the observed Lorentz, the Lorentz factor that we derive is about 10. Okay, so these are very, very relativistic objects. Okay, how are we with time? Okay? So, to conclude, how do I know that jets in gamma ray burst and in AGNs move at relativistic velocities? I see superluminal motions. Okay? I see the spectrum which are highly non-thermal, and in quasar double peak spectrum can give us a limit on the Lorentz factor. I see very high variability, so this gives me a limiting on the emitting size, okay, and on the optical depth of the energies that are emitted. And last, there is also questions of the energies. So here, when I'm looking at the total energies that I observe in gamma ray burst, okay, and I calculate and I assume that everything is emitted spherically. Let's assume that nothing moves relativistically. Okay, let's assume that they do move relativistically, but let's assume that the emission is spherical. Okay, so the emission that I see, I see flux. Okay, so if I want to turn this flux into luminosity, I need to multiply this flux by 4 pi times the distance square. Okay, and the energies that I'm getting, if I'm multiplying by 4 times the distance squared times the duration of the burst, range between about 10 to the 52 ergs to 10 to the 54, 10 to the 55 ergs. So if I assume that everything is emitting spherically, then what I see is energies that are about 10 to the 54 ergs, which is more than which is about the total mass of the sun turned into energy instantaneously. So this is a problem. Okay, this is too much energy coming from a stellar size object. So if I assume that things are jetted, okay, so the energies will be reduced by the size, the area that the jet is covered, the angular area of the jet, divided by the total 4 pi. Okay, so if the jets are very narrow, then this energy will be reduced by the angular size of the jet divided by 4 pi. And the angular size of the jet is about something like 10 degrees or something like that. Okay? So the total energy are reduced from 10 to the 54 to about 10 to the 51, 10 to the 52, which are more reasonable sizes. However, this means that if things are emitted in a jet, okay, this means that I will only see the fractions of gamma ray bursts. Remember, we have relativistic beaming. So I will only see the fractions of the events that are pointing toward me. Okay? So if I take the number of events that I see, okay, and the jet has an opening angle of about 10 degrees, then the actual number will be multiplied by a factor of 100. So this number is a little bit smaller than the total number of, never mind, I don't want to confuse you. Okay, so forget that. So the only thing that I wanted to say here is that the fact that I have jets means that the energies that I see are more reasonable, have more reasonable size. Okay. Okay. So we said that we discussed about relativistic motions within the jets. We discussed about the size of the emitting size. Okay. So the emitting sites of the jets means that their sizes are about gamma squared times the variability that I see. Okay? Now these sizes, if I take the variability that we saw before, then this translates to about 10 to the 7 centimeters in gamma ray bursts, okay? And to about 10 to the 13 to 10 to the 15 centimeters in radio galaxies. Okay? Now, these are very compact objects, okay? 10 to the 7 centimeters, okay? This is about, let's say it's something like It's something at the size of about a white dwarf. No, it's 1/10 of a white dwarf. Okay, 1/100th of a white dwarf. Okay, so this is 100 kilometers. Okay, so again, I need an object with the size of 100 kilometers that can give me that much energy. So this doesn't leave me too many choices about what can emit. That's what can produce these jets. So if I look at stellar size objects, a star is the size of about 10 to the 11. Okay, white dwarf is the size of 10 to the 9 centimeter. Neutron stars is a size of about 10 to the 6 centimeter, and a black hole with 10 solar masses is a similar size of about 10 to the 6, maybe a little more centimeters. So the problem is that these jets, that show this high variability, can only be emitted from a very small locations, and this leaves me with objects that can emit these jets that are very compact. And the two types of compact objects that I know of are, of course, black holes and neutron stars. So that's why we say that relativistic jets are emitted from compact objects. So the fact that I see a relativistic jet immediately tells me that the object that emitted it needs to be very, very compact, because only these types of objects can give me this such high variability. Okay? So relativistic jets can be emitted from only two types of objects, a black hole or a neutron star. In the case of galaxies, I don't know of any neutron star that can give me a radius of 10 to the 13 centimeters. So the only option that I'm left with is the supermassive black hole at the center of the galaxy. Okay? So within galaxies, the engine of the jet can only be black holes, but within gamma ray bursts, I can still sustain both a black hole and a neutron star. Okay? So this is all I had to tell you. I had to give you about jets. There are many open questions, okay, that we have. For example, we see the jets, but we do not know how they are powered. We have some ideas. I'm going to discuss about them tomorrow, but we're not sure. Okay. We don't know what's the launching mechanism of the jets. Initially, when I get some energy that is released, this energy prefers to be emitted over a large angle. Why do jets are so narrow? Okay. How this energy release that is naturally comes out of like over 4 pi will be compressed into a very small opening angle. How the jets are formed? This is another open question that we don't really know. I showed you that in radio galaxies, jets maintain their integrity over hundreds of kiloparsec, and they are very, very narrow. I'm finishing. How is this happening? Okay, how do jets maintain their integrity over such a long distances? We're going to talk about this tomorrow. The jets, we think that jets are produced through electromagnetic processes, and I'm going to show you electromagnetic processes like creating a pointing flux is the most efficient way to extract energy from a black hole. But the problem is that pointing flux is very clean energy. The wavelength is very, very long. These are very long wavelengths. This is radio wavelengths. So how does these radio wavelengths are transformed into the gamma rays, into the X-rays, gamma rays, and UV photons that we see? How does the energy is dissipated? This is another open questions that we don't really know the answer on. Again, we have ideas. The jet don't propagate in vacuum. The jet propagates in medium. Okay? Within stars, the jet propagates within the envelope of the star. In galaxies are surrounded with clouds of gas, so the jet propagates within this gas. So they need to affect it. They carry a lot of energy. This energy is dumped into this medium. What does it do? How does it affect the medium? Okay, it's another open question that we have with jets. What types of high-energy particles are produced? Can jet produce ultra-high energy cosmic rays? How do they do that? This also coincides with the dissipation questions. Okay, so there are many, many questions that we have about relativistic jets that we still do not really have the answer on. Okay, some of these questions I'm going to talk about tomorrow. Okay, when we dive into the physics of the jet. There are many challenges about how to do that. If we want to simulate that, one of the main problems with simulating jets is that the huge scale difference that we have. We start from a very small black hole, very compact object, and we reach distances of 10 to the 6, 10 to the 7, 10 to the 8 times of the original size that we started the jet from. This is something that is very hard to model. It is very hard to simulate for those of you who are running numerical simulations. Okay, so we need to compensate for that. So I'm going to discuss these types of questions tomorrow, and hopefully by that time tomorrow you will understand jets better. So, thanks.
In active galaxy nuclei, the problem that the size of emitting object is smaller than the event horizon is solved when we multiply CA by gamma by Lorentz factor squared, or not?
So actually, it's not really solved. Okay, because the problem is, well, it's depending what you assume on the origin of the emission. If you assume that everything is emitted from within the event horizon of the black hole, remember that in the problem in the toy model that I gave you, I assume that this blob is already moving within a Lorentz factor of gamma. The question is how it accelerated, how it reached that velocity. So if you assume that everything is emitted from the event horizon of the black hole, okay, you need this. There is time that it takes the photon to accelerate to the Lorentz factor that is happening. So during that time, things are not yet really relativistic. So over there, you don't really have this 1 over gamma square compensation. If you want this to happen, you need somehow to get your jet to produce regions which are roughly on the size of this event horizon, which are already moving within Lorentz factor of gamma, and this is something that is very hard. Okay, so the actual problem that the size of the emitting site is smaller than the event horizon is not really solved. What we solve with this model is mainly the compactness, the high optical depth problem.
Or
is there any way to achieve, like, I don't know, I guess turbulent effects or like vortices and kind of use that to increase the size of the center?
Is there any way to see vortices? So one of the ways that we may be able to do that is by trying to measure what is known as Faraday rotation. Okay, if you look at if you have your emission site, okay, let's say that this is my emission site, okay, and I'm located around here, okay, and photons that are let's say photons from a source that is located behind this, let's assume that this thing is optically thin, are coming to the observer. They will be scattered on magnetic fields here, and photons that are scattered on magnetic fields has their I lost the name. What? Polarized, yeah, they are polarized, okay? And the polarization angle rotate, okay? And the rotation is, the angle of rotation is affected by both the magnitude and the geometry of the magnetic field lines, okay? So if you are able to see sources from several locations within this site, and you see different rotation angles, you can derive something about the geometry of the magnetic field, and this is one of the way to get some constraint on the amount of turbulence that we have. Otherwise, you need to have direct imaging of this location, and this is hard.
Probably is a naive question, but for what concerning the acceleration region at the let's say at the beginning of the jet. Okay, so when it gets so fast, could it be
How they accelerate? That's what you ask?
also possible that there is, for example, like the actual starting region of the photons and of the gas is actually bigger, and then it is collimated, for example, by an effect due to the magnetic lines, and the fact that there is especially for AGNs, there is the lasting effect on the field lines.
So that's a very good question. The reason why it's a very good question because I'm going to talk about it tomorrow. I'm going to talk tomorrow about how jets accelerate and how jets are collimated and how magnetic fields can help us with the collimation. So wait with this question, and tomorrow I hope I will give you the answer. Yes? Sorry?
Are there observed signatures of particles like neutrino from this planet?
Observable signature for particle acceleration, that's what you asked?
Particles like neutrinos and other.
Ah, okay, observable for the existence of neutrinos in the jets. This is hard. So the problem is that we don't even know the composition of the jet. Okay? All we know that in order to reach very high Lorentz factor, you need to have a large energy dumped into a very, very light material. Okay? If you calculate, if you take the total energy within a jet of a gamma ray burst, which is 10 to the 51 ergs, and you want this energy to accelerate matter to a Lorentz factor of 100, okay, then it means that the amount of mass that you accelerate is 10 to the 51 divided by 100. This is 10 to the 49 ergs. 10 to the 49 ergs is about, this is total rest frame energy. Okay, so this is about 10 to the minus 5 of the total number of protons that we have in the sun. Okay, so we need a very, very clean jet. We do not know the composition. A way that we can tell the existence of neutrino is not from the jet, but actually from the jet cocoon. Because the cocoons are not so relativistic. And if we will be able to observe emission coming from cocoon, and some say that we already have in the recent event, in the recent short gravitational wave short GRB event, some say that we already have observed cocoons. The emission there, from the emission there, we can deduce the existence of neutrino through the spectrum. I may touch that a little bit in the third talk.
For this question, sorry, we have no time. For this question, because it was necessary to study. But no one knows what the species.
Yes, we do not know the composition of jets. Yeah, until today. Maybe we will never know. Yes. Yes.
That we see
Yes.
some lines. And
Yes, maybe we will never know.